Believe it or not, we can actually add up an infinite sum in certain situations. And in other situations, we can at least show that the infinite sum exists as a finite number, and then we can estimate it. An infinite sum is called an infinite series. This rather unintuitive name is forced on us by tradition. One of the oldest infinite series was studied in ancient times and is called the geometric series. Take any fixed real number r, and starting with r to the 0 equal 1, add up the successive natural number powers of r. That is, 1 plus r squared plus r cubed, and so on. In fact, to be really down to earth, I want to choose r equal 1/3. So we are dealing with the infinite series, 1 plus 1/3 plus 1/3 squared plus 1/3 cubed, and we keep adding these powers of 1/3 forever. Of course, you can see one problem right away. No human, in fact nothing we can construct, can add up an infinite set of numbers. So right away we are forced to look at finite sums, and then we try to see what happens as the finite sum gets longer and longer. These finite sums are called partial sums of the series. For this geometric series, we would have the set of partial sums 1, then 1 plus 1/3, then the sum 1 plus 1/3 plus 1/3 squared, and so on. This is just a sequence of numbers 1, 4/3, 13/9, and 40/27, and so on. So we have reduced the problem of making sense of an infinite series to the question of the convergence of the sequence of partial sums of the infinite series. Now, in fact, the numerical work we just carried out doesn't really tell us much. It turns out it is easier to see what is going on by working with some abstract mathematical ideas and notation. So, with the aim of deciding whether the geometric series makes sense, we look at the general geometric series and its associated sequence of partial sums. We will use summation notation to make our formulas and equations easier to write and to read. The series 1 plus r squared plus r cubed, and so on forever, can be reduced to summation k equals 0 to infinity of r to the k. Don't be intimidated by that symbol infinity in the summation. It just means that we don't stop. And what that really means is we have to look at the sequence of finite partial sums, which we label S0 equal r to the 0, that's 1. S1 equals r to the 0 plus r to the first power, that's 1 plus r. S2, the partial sum S2 is r to the 0 plus r to the first power plus r squared, summation k equals 0 to 2 of r to the k. And in general, the nth partial sum is labeled S with a subscript n called Sn, and that's the sum from k equals 0 to n of r to the k in the case of the geometric series. We will say that the series converges when the sequence of partial sums converges. It turns out that for the geometric series, we can show exactly when this happens and give a formula for the limit of the sequence of partial sums. That is, we can give an explicit formula for the sum of the geometric series. We write Sn, which is 1 plus r squared plus, and so on, plus r to the n minus 1 plus r to the n, and then we're done. That's Sn. Now multiply Sn by r, so you have r times Sn is r plus r squared plus r cubed plus out to r to the nth plus r to the n plus 1. Now notice that these two sums are quite similar. The sum r times Sn doesn't have the lead-off 1, but it does have the extra term r to the n plus 1. If you subtract these two identities, and notice all of the cancellations on the right side, then you get, at least when r is different from 1, Sn minus r times Sn is equal to 1 minus r to the n plus 1, which is equivalent to, by solving, Sn, the nth partial sum of the geometric series, is the ratio of 1 minus r to the n plus 1 divided by 1 minus r. So, to recap, if we add the terms of the geometric series up to and including the term r to the nth, we will get the fraction 1 minus r to the n plus 1 divided by the term 1 minus r. In the special case when r is 1, we would have got 1 plus 1 plus 1 plus 1, n plus 1 times, which adds to n plus 1. So clearly, when n equals 1, the partial sums just get larger and larger and do not converge. So the geometric series makes no sense, i.e., the series does not converge when r is 1. Since the partial sums get larger and larger without bound, we also say that in this case the geometric series diverges to plus infinity. Now look at the situation when r equals 1/3. We have an explicit formula for the partial sums. When r is 1/3, the partial sum Sn, remember that's just the sum from k equals 0 to n of 1/3 to the kth power, is exactly the ratio of 1 minus 1 over 3 to the n plus 1 divided by 1 minus 1/3. Since the limit of 1 over 3 to the n plus 1 is 0 as n goes to infinity, we know the limit of the partial sums Sn for this case of the geometric series. The limit as n tends to infinity of the Sn's is exactly 3/2. And to re-emphasize how we arrived at this result, what this is really saying is, if you add up the successive powers of 1/3, the more terms you add up, the closer you will get to the number 3/2. If we go back and repeat our early numerical work, we had S0 is 1, S1 was 4/3, S2 is 13/9, and S3 is 40 divided by 27. Now the actual infinite sum is 3/2, that's 1.5, while S3, 40 over 27, is approximately 1.48. So S3 is already pretty close to the actual sum. Now we need to recall a simple result from our earlier study of sequences. Given any real number r, the limit as n tends to infinity of r to the nth power is 0 if and only if the absolute value of r is smaller than 1. The limit is 1 if r equals 1, and the limit does not exist otherwise. So we know exactly when the geometric series does or does not converge. Namely, the geometric series summation r to the k from 0 to infinity converges to 1 over 1 minus r, if and only if absolute value of r is less than 1. The series diverges, that is, the partial sums do not converge to a finite limit in all other cases. There is one small extension of the geometric series I should mention. Consider the series summation k equals 0 to infinity of minus 3 times the power 1/5 to the k. This looks like a geometric series, except for that annoying minus 3 in every term. But the minus 3 factors out of every partial sum. So the limit of the partial sums of this series is just minus 3 times the limit of the partial sums for the geometric series. Now the partial sums of the geometric series sum to 5/4. That's summation k equals 0 to infinity 1/5 to the kth power is just 1 over 1 minus 1/5, and that's 5/4. So we can sum the original series, factoring out the minus 3 as if it were a finite sum. The summation from k equals 0 to infinity of minus 3 times 1/5 to the k is just minus 3 times the sum from k equals 0 to infinity of 1/5 to the k. And that's minus 3 times the ratio of 5/4. So in general, summation k equals 0 to infinity of a constant a times r to the k is just a times the ratio of 1 to 1 minus r. A second point worth mentioning. Suppose that the sum doesn't start at 0. For example, suppose we are dealing with the summation from k equals 5 to infinity of r to the k. That's r to the 5th plus r to the 6th plus r to the 7th and so on, going on forever. And you see that we can factor out r to the 5th. And we have r to the 5th times the geometric series 1 plus r squared and so on. And so that's just 1 over 1 minus r times r to the 5th. So we have no difficulties with this situation. For example, the summation from k equal 5 to infinity of 1/4 to the kth power, that's 1/4 to the 5th plus 1/4 to the 6th and so on, is equal to 1/4 to the 5th times the ratio 1 divided by 1 minus 1/4. And that's just 1/3 times 4 to the 4th.